And how is it yet needed? Oh, he knows. He knows.
Like I did some these so you have like a magnet in the pendulum and it swings around. And you have a magnet in the and it creates like current.
Oh, I don't know.
I think it's a really cool question.
No reason why it's a band magnet because I don't like vibration. No, set.
You know the
Which one?
the
I will.
he's the guy who's doing this with you know like the German like cover?
Yeah, pump.
What?
Pump.
No.
No. Pump.
He said he proposed like the lead vocals. The believe in the
Elmo. Same. Like also on the phone, as I said yes. I don't see a couple of pages. I'll be saying I'll be disturbed.
and like
I have seen human life. So back the first one, and the position, they did in the way I left.
yeah, like I watched it. It reminds me of
It's fast, it's quick, it's nice, and how she attached to the back. Yeah, or just talk about type of the projector.
you know the Falcon? Yeah, I watched him. I didn't watch it.
Oh, but I really like we might not snake. Like I worked on different countries too. They were like,
We're not gonna lie. Watching screen was
I know.
they were really slow. Like Shirley, she took like 25 seconds to explain one second back.
I can't think that. I know why. Like, I'm wrong.
Like she was talking to me, she was enjoying it, she was taking her time.
I know. I'm wrong. This is all possible too. I don't know how it does. When she is working for, she might not be on this level. She's not on this level. I'll be honest. Like she's like my last couple of days. I'm working like 3-4 hours. They don't the other things of the school. Like when you gave me job
A few weeks ago. Before we had done like DPI years. What? I competed.
Oh,
Okay.
okay. I met many people that I competed with. Every work is
How do you know you?
like the shop, the Omar.
Yeah. Over something.
Good morning, my name is Jacob, and today I would like to present you our solution to the problem number 9, magnetic axis. So the problem statement is that one of the magnets is non-magnetic and non-selective base such that they attract magnetic energy from the spring. Investigate how the motion of the moving magnet depends on the relevant parameters. So here we can see a demonstration view. And to just give some basic explanation, there are two important active forces. There is the gravitational and magnetic force, and what they affect is both the rotation of the magnet around with the string and also around the point with around the point where it is connected to the string, as you can see in the background. We will investigate several types of motion. So there will be the motion in a single plane, motion of a singular magnet in several planes, and motion of a magnet in between two attached magnets. We have altered several parameters such as the distance between attached and hanging magnet, the amplitude of oscillations, the strength of the attached magnet, this number of attached magnets, so 1 or 2, and lastly the distance between attached magnets. Let's look at our setup. So there are some parts which are obvious from the problem statement, such as the string, suspended magnet, or attached magnets. And also there is the electromagnetic release mechanism, which is for like a repeatable measurement, so we can always release from the same position. We have measured the magnetic moments, as we have used dipole approximation, and we use force multiplier. So let's look at our theory. Well, we start off with something very simple, and that is called Newton's second law, with three main forces acting, and it is the magnetic force, the gravitational force, and the tension force of the string. Now, and one more thing that I would like to note is that, again, we use magnetic dipole approximation, so this means that we have each magnet has this dipole moment, which basically means what is its strength. So, and we have to use this in order to model the magnetic force. Now, in some of our experiments, not all of them, we needed drag. And so for these measurements, we have fitted a laminar drag, as the Reynolds number is slow enough that we can assume a laminar flow around the magnet. The magnet is rotating throughout the motion. To model this, we took the gravitational torque, magnetic torque, and this Euler rotation formula, which tells us like how the angular velocity changes. And this is the rotation matrix for the direction of the magnet, which we have like altered over time, and we simulated this with Euler. So let's look at movement in a single plane. Now, at start, we start with something very simple, and that is the small oscillations of this magnet. If we simplify our theory for this case, we receive these two differential equations. So this is just for small angle oscillations in one plane, and we receive the differential equation, and the analytical solution has several angular velocities. Well, two of them. We take one of them, which was dominant in our case. This is the final equation for it. It's quite long, but the thing is that it's analytical, so we didn't have to simulate this. And from this, we have received our graph of period and distance between the magnets. So on the x-axis, we can see the distance, and on y, the period. One qualitative thing to note here is that when they're close to each other, the period is small. As you can imagine, the forces are way greater. And as we increase the distance, it kind of approaches some asymptote. Well, it's quite natural to think that this asymptote, as you can see, is the period of a standard gravitational pendulum, because, well, the magnetic force is becoming negligible. For more complex cases, we had to use a simulation. On input, we use magnetic moments, the position at the start, and the string length. Also, the distance of the magnets and the mass of the hanging magnet. Here you can also see this like red thing going around. That is the direction of the magnet as it changes during this. For some experiments, we also use the graph coefficient. But for example, for this one, we didn't really need it, as this is the graph of the amplitude versus period, and this is just during one period of oscillation. And for this reason, this is our graph, where we can see that with increasing amplitude, the period increases too. So this is our graph for the amplitude versus period for different distances between the magnets. And maybe if I could tell you qualitatively what is happening here is that the same thing as I have said before. The greater the distance between magnets, the greater the period as the magnetic force is lower and the lower forces are acting. And this last graph shows us how does the period increase with increasing amplitude. Now, that was for the movements of a magnet in just a single plane, but there's more to this problem. That would be the movement, for example, of a single magnet in 3 dimensions. Now, for this case, we just took the experiment and simulation. This time we use the fitted air drag, and from now on we will have to use the air drag as for the additional experiments we needed it for a simulation. And we can see at least the qualitative mesh. Maybe I can tell you later about what is the reason why I'm only showing you the qualitative mesh. And lastly, we have the movements of 2 magnets in 3 dimensions. Such movement can be divided into 2 parts. In the first part, the magnet moves in between the 2 magnets, and then when it loses enough energy, it gets trapped around one of the stable points, usually around one of the magnets. Now, I said that there's like a defined something called transition time between the phase 1 and phase 2, and in order to be measurable or used in our simulation, I defined it as the last time the magnet crosses the line between the attached magnets. Now, so this is the transition time for both our experiments and simulation. So, this is quite an interesting graph. You can see several things here. Well, first up, you can see that the error bars are very huge. Well, what is the reason for this? Now, the reason for this is, as I will tell you later, this system is chaotic, and for this reason, even with the magnetic release mechanism, the magnet always has a bit different initial condition, and for this reason, it takes a different time to stabilize around one of the points. So this is caused by the natural variance of the experiments, not by error. Also for the simulation, we have released it from several points which are like close to each other. And for this reason, you can see also the variance of the simulation, with each point representing something by a single millimeter and so on. So there are stable equilibrium points in which this case can stabilize at the end of the motion. Now, this is a graph where we have calculated the stable equilibrium points versus the distance between the attached magnets. So, at first, when the magnets are close to each other, there is just one stable equilibrium point in the middle. If we increase the distance a bit, so this is in most of our cases, there are 2 near each of the magnets, and if we increase the distance furthermore, there is a third one in the middle. Lastly, the 2 ones with the magnets on the sides disappear, and we only end up with the one last equilibrium point, which is stable. Also, here is also an equilibrium point, but it is unstable. So, what is this graph? We took our simulation and we simulated it from different starting positions, and we wrote down what are the different stable equilibrium positions where it ended up. Now, there are several regions. In the first region, it is it's very much changes with the initial conditions. This is due to the chaos I will mention later. And then in some other cases, it always ends up near the nearest one, as this one is the only one that has energy to end up in. It doesn't have energy to flip to the other one. I have made an experiment for this, just for the 1/4 of the field, as this is a symmetric case. So for this reason, I didn't really need to do it for the whole diagram, and we can see that it meshed. In some cases, it could have done to both of them, although it wasn't although I released it from the same positions, and in some cases, it only ended up in the nearest one. And here you can see an overlay for the whole board. So this is still from 1/4, but I overlaid it on the whole map. The thing that I guess every one of you is asking is, well, I'm talking here about the chaos. Now, we need to quantify the scale somehow, and the indicator, the quantifier of chaos, is the Lyapunov exponent, which basically tells us how exponentially increases the distance between infinitely close points. The problem with it is that it's like, you cannot make this experiment, you know, you cannot make two infinitely close like experiments and then calculate how they depart from each other. So the way this is standardly done is that we use some kind of algorithm for this. The one I have used is called the Rosenstein algorithm, and it is an approximation for this. And we can, it only needs one trajectory. So I have given one trajectory for this algorithm in both single magnet case and double magnet case, and in both of them it seems that our system is scalable, as the Lyapunov exponents are positive and matching. So the Lyapunov exponent is positive, therefore the system is scalable. Lastly, I have done this beautiful picture. So what is this? I release the magnet from each of these places of the map, and I observe the first 2 seconds of movement, and I run the Rosenstein algorithm on this, and the result of this is this map which shows us the Lyapunov exponent based on the position. So the color is for the Lyapunov exponent. To conclude, these are the possible sources of systematic error. So they could be the attachment of the magnet or the measurement of magnetic moments. And it seems I don't have the time for conclusion, but I've done the explanation, matching model, ultimate.
Thank you so much for your report. First question I would like to ask you is, you mentioned one of the parameters is the release position, right? And you used the release position thing to release it from one point, right? Is it adjustable? Like, can we adjust the release position of the magnet?
Yeah, of course. Where is it? It's like attached to
Okay.
something, but
thank
I can change the release position.
No, we'll discuss it later.
Yeah, I can change it. That's
And
the short answer.
on slide 30, you mentioned 2 stable points for the magnet when there are 2 fixed magnets, right? Can you please tell me the conditions apart from the placement of fixed magnets when we can have 3 stable points, not just 2 stable points at both the magnets?
Well, there can be 3 stable points if there are 2 magnets. So there is one on
Yes, apart from the placement of fixed magnets.
Well, it also probably depends on height of the hanging cable, strength of these 2 magnets.
Strength.
And
Okay, we can discuss it later. Thank you so much. And due to Lyapunov exponents, you said some values should be positive for motion to be chaotic, right?
Yes.
What are those values?
yeah, so here are the values I calculated for these.
Can you please go back to the graph?
This one?
Yes, this one.
So these are the values based on the color.
Okay, so you assume the motion is always chaotic because we don't have any negative numbers.
Well, I didn't assume it. It came out as this from the simulation.
Okay, thank you. And on the page 22, you show the direction of the magnet. What does it mean? Direction of the magnet. Is it the direction of the magnet?
Yeah, the magnet moment is awesome.
Okay, thank you so much.
So,
The problem states that you have to attach one or two magnets to a non-magnetic, a non-conductive base, and magnets should attract the magnet suspended from the string. We have to investigate the motion of moving magnet and the relevant parameters. First of all, I would like to say the contents of the review of the report. We've seen some parameters, we've seen a few experiments conducted, and we've seen the Lyapunov exponent, which was partially explained. And at the end, we've seen the conclusion, which is good. We could conclude all our experiments and how do some parameters affect the motion of the suspended magnet. About the strengths of the report, we've seen some relevant parameters investigated and we appreciate it. The simulations match the practical data. This is a good point. Our system is very chaotic and we like that there was explanation of calculating exponents to see whether the system was truly chaotic and stated. This is good data analysis. But we think you could have added some more relevant parameters. Then on the slide 28, the origin of simulation was not really explained, and also we didn't really understand about the chaotic motion. If you have only one type of motion, or did you observe any other types of motion, I would like to discuss it. Also, will we yes, and the areas of improvement, we didn't really understand the stable position, the position of equilibrium when we have two magnets. I think you could explain it a little bit more because it's one of the big parameters as stated in the problem, and I think you should have talked about it a little more. And about the equations, we believe that the equations were not really explained. How did you derive them? Where did you get them from? How does it how is it relevant to the experiment? And what relationship does it show with your with the motion of the suspended magnet? And also. You didn't really show the stable position in the middle. In one of the graphs, we would like to discuss it. Those are our discussion points. The equilibrium between magnets, as I mentioned, then we would like to, about the spelling, the Lyapunov exponent. And then we would like to discuss about the release position. And the uncertainty, we didn't really understand uncertainties on slides 20, 23, and 24. And also we would like to discuss a little bit about parameters. Maybe we could add some more because we believe there are much more parameters to explain. Thank you. Let's move on to the discussion.
But in my opinion, simply we chose the one we
can you please go back to this second slide?
Okay.
There you mentioned the force of the suspended magnet. Does it mean the force that you apply while pushing the magnet, maybe when it's when it's close into the magnetic field of the magnet, or is it force that is no, the slide that you just showed me about other parameters.
Oh, of course.
Yes. Because
yes,
we believe as it adds up the potential energy to the system, and therefore the overall energy of the system will be more, and therefore the motion will be significantly different.
Okay, so these are the other parameters. This is one.
Yes, can you please talk a little more about the force of the system? What do you mean by force?
Yeah, so I mean the magnetic moment. This is like.
Is it the initial force? Like
No. It's
how
like,
you push the
what I
magnet?
mean by this is this, like not force as a physical quantity in the F is equals to A,
Okay.
but simply it's like intuitively when you say force of a magnet, what you actually mean is the magnetic moment.
So you mean the acceleration of the
It's like
magnet
the
during
size of
motion?
the magnet.
The size of the magnet.
Or how strong is it?
How strong is it? The force of the magnet. Oh, you mean the magnetic force of the system?
Yeah.
Oh, okay.
But
thank
we
you.
have changed the attachment.
So you changed the diameter of the magnets, right? You used only the neodymium magnet as I seen in the power zone.
Yeah, I have changed the attached magnet, but not the suspended one.
You didn't try any more suspended magnets.
I think that this is a better parameter as if I change the suspended magnet, this also changes the mass, and therefore we didn't really separate these two.
So you think the mass of the suspended magnet is not a relevant parameter?
No, I think that if I change the size of the magnet,
Yes.
of the suspended one, then I would both change like how strong is the magnetic force and also how heavy it is.
I believe it would be more decent to change the diameter of the suspended magnet, because we will not only change the force, but also the mass. I think the motion would be more dropped, you know, the
I
magnet will drop
disagree
more.
with you, but the reason I disagree is that I think that we wouldn't separate the parameters of the magnetic force and the weight.
But you changed the force of this magnet,
Yeah.
right?
Yeah, so this means that I separated the force that was pushing it down from how heavy the suspended magnet is actually moving. So then we actually change two things in our equation. We couldn't separate such parameters.
Okay. Then can you please go to the slides 20? There was a drop.
Of course.
We didn't really understand the uncertainty. You see, the uncertainty are like really varying for the different distance between magnets. Can you please explain a little more? Why is it so? The uncertainty itself, why is it like?
Yes, it's caused by the uncertainty of measuring the magnetic moment.
So there are uncertainty in measuring the magnetic moment.
Yeah.
When you increase the distance
So
between
this is the equation,
Yes.
and you can see that it's quite big because each of these is like substituted in here. So it's a very big analytical equation, and for this reason,
For this reason, the magnetic moment is changing, right?
yeah, and the magnetic moment is the parameter that has like uncertainty. Well, we know exactly what is the vacuum permeability.
Okay, thank you so much. Can you please go to slide 30?
Of course.
You've mentioned about the stable points, the equilibrium of the magnets, of the suspended magnet, where there are two fixed magnets, right? And you, during the short questions, you said that one of the relevant parameters that would affect the motion, it was the amplitude, if I'm right?
Yeah, but I measured the amplitude of oscillations about this singular magnet, as I'm not sure how good I define it when moving around two magnets.
I'm talking about the starting position.
Oh, starting.
Yeah, if you vary the amplitude, you know.
What do you mean by amplitude of starting position?
The height you
Yeah.
release the magnet from.
No, I haven't, because I said there are many parameters that could have changed, and these are the ones I thought are the most important. But in this case, I think it was like 3 centimeters.
Yeah, can you go next slide, please? Next. Just about the
So here are two magnets, and in this case, we have two stable positions. So
Yes.
maybe an intuitive way to explain this would be maybe through like the potential energy.
Yes.
So what happens here is that if you look at the potential energy, in this case, it will do something like this based on on this axis,
Yes.
the x-axis, and there's also an equivalent one in the middle, which is
So it
unstable.
goes a little bit down as well.
It is
If there's an equilibrium.
no, this one is like unstable,
It's unstable point.
and these two are
When the magnets are close together, right?
yeah, and these two are stable. If we increase the distance even more here on this graph, we can
Yes.
see that here a third equivalent point appears, so the graph may look like
Do you have the limit when this graph converts into this graph? Do you have the limit when
Yeah, it's
the
like-
distance between magnets when
it's like here.
start?
Here, this is calculated from the forces.
Oh, okay. And after this point, there are no stable points
On the sides, yeah. So the way you can imagine this is that if the magnets on the sides
Yes.
are very far away, they don't even have a significant effect.
I partially disagree with you because we believe that if the magnets are strong enough, they have a stronger magnetic force,
course.
and therefore we can have the stable points on the sides, and
Yeah.
therefore it's kind of
Imagine a situation like this. So the magnet is hanging like here,
yes.
and the magnets which are on the sides, if they were, for example, on the other side of the room, you can imagine that they're so far away that they don't have the effect of the magnet that is hanging anymore.
Okay, so the distance you show is
The distance between the attached magnets. So
between attached magnets.
between these two magnets.
Yes,
This one remains in the same like
but
length.
you're talking about the fixed magnets. Okay, let's move on.
Like if I had
Can we please talk about the release position as well? You mentioned something about the amplitude, right? When we discussed the short points.
this one with this graph.
No, can I ask, are there any other parameters that could affect the motion? You talked about the amplitude. Is this the amplitude of the motion of the magnet, how it's
So
right?
I'm not sure what is your definition of amplitude. To
Amplitude
me,
is the
what I
distance.
mean is that in this case, here we have an oscillatory motion. So
So this is the distance between fixed and suspended magnets.
so this is like the color is the distance.
Okay.
The y-axis is the period because in this case
Can I
we
please ask how did you vary the distance between magnets?
well, I simply increased the height of the pivot point without changing the length of the
You increase. So your control variable was the length of the pendulum.
not the length, I increased like the touch point.
Yes.
The length of
So
the
your
string
length was
same.
controlled. You didn't
Oh,
change it. You didn't change the length of the pendulum.
I didn't change it.
Okay, I agree with you that we shouldn't change the length. The conclusion of my position is that I don't really agree with the stable position of the magnets, the graph. I don't think that 35 centimeters is enough, and it's all we can change it, and we believe that initial force is significant, that they didn't really talk about the initial force. As I said, it will add up to the overall energy of the system, and therefore the system, the motion of the suspended magnet will be different. And also, they changed the yes, and also the uncertainty. We actually agree with the reporter. I understood.
Bye.
Thank you.
Okay, questions from the reporter. What do you think is the assisting in the phenomenon?
Well, the force is not only gravitational but also magnetic.
Oh, so you think that the motion is more important? The motion is related to the period or the trajectory. Is the trajectory more important or the period?
Well, we have like this is quite a wide problem, and we have observed like both the trajectory and the period, and I think they're both important for this problem. Like,
Okay, questions for the opponent. Do you think that a single magnetic case will be chaotic?
Single magnetic case.
Yes.
If the magnetic force is stronger, then yeah, it could be chaotic, but it also can
Okay,
be
questions for the reporter. Do you think that in linear motion, a single magnet will be possible?
what do you mean?
A linear motion, because
Linear. What would you mean? Oh,
like
so well, if we don't give it any initial like, rotational velocity, it doesn't have any reason to start.
have you ever considered a lateral force on charged particles moving?
Yeah, I think that's like negligible.
Okay. Okay, so how many dimensions are your electron exponent?
Like for the calculation,
Yes, for the calculation.
well, only a single one, as a Rosenstein algorithm only works with a single one, and this one is distant from the center of this magnet. In this case, it is distant from the center in that magnet.
Okay, questions for the opponent. I believe that the diagonal exponent only explains the sensitivity to initial conditions. Do you agree?
Yes.
And what do you think is the chaos is in
What
is
is
it
the
transient chaos or permanent chaos?
Chaos.
Yes.
Chaos is the motion when the initial conditions are a little bit different, then the motion will be like really different and partially
Okay,
unpredictable.
do you agree that there will be more criterion for the definition of chaos?
I'm sorry, can you?
Okay, thank you. Okay, for
You may comment that this is transient chaos, as when the magnet damps, it always ends up in the same position. So it is.
okay, thank you. Page 23. In page 23, is described an analytical solution.
No.
Okay, so this is solving for a numerical
This is
solution.
numerical.
Then how do you account for the period in numerical solution?
Well, I basically like use sci-fi peaks. It's like I take the
Did you
period
do
of
a discrete
oscillation.
Fourier transform in your? You do a discrete Fourier
No,
transform.
I don't. I just find the peaks and there doesn't seem to be other people.
Would you agree that in a simple harmonic case, a small amplitude will not influence the period?
Like, well, this case is simple harmony only with small amplitude.
Small amplitude, so you will not influence the period.
Well, no, because it's small. Well, as long as it is small, it's like harmonic.
Okay, thank you, guys. problem statement. And I think the key questions will be the equations of motion describing the system, which are pretty light about the recorder, which we have right now the equations of motion. And the orientation of the pendulum magnet is also considered in their equations of motion. And relevant parameters will include the number of magnets, the geometry of the magnets, the release condition, and the string length. However, I think the most important missed part on both sides is the assist, which is clearly stated in the problem. Okay, so this is the reporter's overview. They have covered 3 types of motion, including planar motion, flower motion, and the 2 magnets case, where they have clarified that it is transient chaos. And there will be a 2 movement case for the 2 magnet case. However, they have not covered a reason for the flower motion, as the lateral force will be needed to make the magnet move. I believe that there are some missed forces in their equations of motion. And I've also missed the meaning of the assist in the phenomenon, as we have, when we release the magnet will, when you cross through the base magnet, it will turn, causing like a gravitational assist, which needs to be discussed with the trajectory and not the period. So for the theoretical model, they use a dipole approximation using an analytical solution for equation of motion. However, they did not account for the finite size. And for the orientation of the force, they have accounted for the gravitational torque and the magnetic torque. And for the experiment, they have done different magnetic distances, magnetic strength, and they have discussed the 2 attractors in the 2 magnet case and found the fractal Bayesian algorithms. However, I think there is a key misunderstanding of chaos is that the diagonal exponent should be calculated using the phase space, and the other dimensions are not accounted as well. So this is the review of the opposition. So in the presentation, they have believed that the system is highly chaotic, which I disagree in the one single magnet case. It should not be chaos. And there is other motion may be caused by the initial velocity, which I totally agree. When you release the magnets, if you give it an initial tangential velocity, a circular motion may ensue. And the missed parts will be the misconception of chaos and the Lyapunov exponent. And for the short question, they have asked about the Lyapunov exponent values. Although they are bigger than 0, it can only explain the sensitivity to initial conditions. I also question their method of calculating, as the phase space is traditionally needed to be used to calculate the Lyapunov exponent. They have also mentioned the pre-stable equilibrium points, which is quite important in the phenomenon. However, they have a trivial question, which is the initial position change, which I don't think is pretty relevant in this phenomenon. Also, in a discussion, they have talked about the initial amplitude and the control parameters and the first equilibrium point. However, I think they have spent too much time on clarification of the setup and should have even more time to discuss how the assist affects the trajectory of the magnet motion. So these are the discussion points. For the opponent asks, what is the meaning of force of the suspended magnet? The reporter replied that it is not initial force, but the magnetic moments of magnets. And the opponent also asked the changing of the suspending magnets. And the reporter replied that many parameters can be changed at the same time. And this I agree with the reporter, because there are many parameters, including the geometry of the magnet position, which I don't think is quite discussed in the report. And they also asked how the amplitude will affect the motion. This I have already clarified with the report that they use a numerical solution to solve for the period. And for a small amplitude, it will be a simple harmonic motion period. And I think the trajectory should be investigated in this phenomenon, as it is more important than simply discussing the period in the sense of the assist problem. And that will all be my review, and thank you for listening.
So thanks both to the opponent and the reviewers for all the comments, discussion, and everything. One thing that came up during the review and was mentioned is there is actually the sensitivity to initial conditions, the same thing as the chaos. Now this is the definition of chaos, and we can see that it must be sensitive to initial conditions, topology could transitive, and have dense periodic orbits. Now the problem with the other two is that they cannot really be experimentally quantified. Now it could be possible for a rigid mathematical calculation from the differential equations to derive these, but it cannot be experimentally verified. So this for the part of the transient chaos of this problem. So there's another thing he mentioned. Basically, for example, if we have a singular magnet, what this means is that when the magnet goes down and stops moving around, then this system is of course not chaotic because it always ends up in the same position. But in a case there wouldn't be the friction force, then this system will be chaotic, and for this reason, for the short time as it is moving around, not losing that much velocity, this system is chaotic. So also the review mentioned the dipole approximation. We've also tried surface currents version of the approximation, but the problem was that you have seen some of our graphs which are like very complex maps, and this is really like time complex problem. And if I would make a very big map with this, it would be quite complicated. And the problem, and the other thing is that it didn't make a great difference. So the predictions were basically the same, even if we like fitted the force from magnetic dipoles, which we have seen in one of our experiments, it matched well. So thanks to everyone.
Yes, to the reviewer, how many Lyapunov exponents are there in the system?
Well, for me, I think that we should calculate like a 9-dimensional phase space, including the x by z and the mu x y by z. What if they are calculated with 9 dimensions?
Okay, and to the reporter, do you agree? And if so, which one did you measure?
Yeah, so I measured the Lyapunov exponent, which was obtained from the Rosenstein-Algorithm approximation, and well, Rosenstein-Algorithm approximation makes like takes a one-dimensional array because otherwise you cannot calculate the Lyapunov exponent, and it calculates the largest Lyapunov exponent. So this was the largest Lyapunov exponent in the system.
You use two big magnets, okay, extended magnet on each side.
They were.
What was the style of the magnet, and how did you modelize it? The two magnets attached on the ground.
What do you mean, like? Oh, sorry, I didn't like hear the words.
Okay, so you had on the ground two magnets. They were not punctual magnets; they were large magnets. This one.
Well, that's not true. It's like well, they're behind this paper.
So what's the size of the magnet?
Well, it's the same size as this one. You can see like a small circle here on the paper which I sketched.
Okay, and on your chaotic picture,
yeah,
with two domains, you use also the same size of the magnet. On this picture. So you got the two domain, but the magnets.
Yeah, so the magnets are like this big, I think.
Oh, okay.
About.
Did you change the offset of the magnets, or were they always in a line?
Yeah, they were
And
always
the
in
starting
line. So
conditions were-
this is something I mentioned before. There's so many parameters.
Yeah.
Like, this is the one we chose our important
Yeah.
ones. So,
Yeah, not very long.
I've got a question for the reviewer. What do you mean by assist?
I think the assist is referring to like if you imagine a spacecraft flying through space with a gravitational pull, you like pull towards one side. And for this, in this phenomenon, when you release the magnet, even if it is completely linear, it will eventually transition into a flower-like motion due to a velocity-dependent force from the charged particles inside of the magnet, which I don't think that the equation of motion have
I disagree with you. You can see that in our simulation, which only to the magnetic force, we also receive the same kind of motion.
But what is the initial condition of the?
Well, yeah, so it has some initial velocity, which is angular, and for this reason it makes the flower motion.
To the reviewer, since you explicitly mentioned the lacking lateral force to explain the flower motion, can flower motion occur in a general two-body problem?
Sorry,
Can flower motion occur in a general two-body problem, where the force is purely radial?
I think that if you release without the velocity, it cannot occur. However, if you give it the velocity, it can occur.
Questions in the panel?
said you thought the initial energy of the system was important.
Yes.
Yeah, why so?
If the initial energy is higher, then we'll have more energy converted into the kinetic energy, which is the motion, and therefore more motion can result in chaotic motion, even if the forces are small, because we've conducted this experiment and we observed it.
Okay.
Can I just like review what told us about the initial velocity moving? So just to note, here we use this mechanism. We only release the ones with hand, so we have initial velocity, and the velocity in the simulation was then like from back track velocity in the experiment. So that in this we have initial velocity.
And one last question for the review. You were saying that you thought the simple harmonic motion conditions would be for small angles only. So what are the conditions for simple harmonic motion?
I think that the magnet will not have an offset if it is small angles. And so for their theory, they cannot investigate
What are
the
the
offset.
conditions for simple harmonic motion?
I think that the force should be proportional to the x direction. So
Okay, thank you. Is it time so let's go to this graph?
8, 8, 6.
And the scores for the opponent.
Opponent scores are 5, 4, 4, 4, 4.
And the scores for the reviewer.
The reviewer scores are 7, 7, 6, 7, and 7.
Thank you. May I have the score sheet? And we have a 6. We have a 6 from Gavin.
Okay.
Do you have any comments?
I thought it was a very good score. You investigated really well. The only thing I thought was lacking to taking you into the 7 and above territory was the predictive nature of your theory. I didn't think that linked with your experimental values too well. In all but the very simple case.
Yeah, I'm also already thought that I had to justify my hate, and I partially disagree to again because I think that you showed very reasonable that your system is chaotic, and especially you seem to be aware of what the diagonal of an exponent is and how to calculate it, and then clearly demonstrated the sensitivity to initial conditions. And in this context, I mean the theory is not very predictive, but it's not your fault because predictability simply breaks down at a certain degree in chaotic systems. And I think you addressed the point very well, and that is a very well structured presentation that you had a story with, and I really appreciate it.
For the opponent, the score is quite close. We have 5 from me and 4 from other girls. For me, I give 5 because we have a good, maybe a little bit cool about the summary, but not the discussion period. I want to discuss more about the fundamental physics, right? For example, why the initial force, impact the S, the phenomenon, or and the version of a particular time, or the gives off. Maybe you can give the floor.
Not much explanation. Just stick to the scoring sheet. I gave 1 most everywhere. It was.
It's quite a
Yeah,
close
it's
score.
difficult for me to do more than this.
For the rule, we have 6 from Pedro.
Yes. I think I actually was at 6.5. I think the reason was quite good, and I think the discrepancy is not too large, but I think what ultimately, like the point about the lateral forces and what you meant by that wasn't very clear to me, because I mean this non-closed off can generally occur without strict force in some non-regular direction, so I really didn't see what you were trying to address. But I mean overall I think the reason was quite good.
Okay, thank you. Gavin, you give us 7.
Yeah, I mean, I thought we addressed all the major points that I was keen to ask. For review, again, focus on both sides quite well, and answer to my questions and other jury questions I thought was really good, so it was almost
Thank you. Now we have finished this morning's work. Thank you.